What are you doing?
はい、東京
I'm
試験
doing
は
permeability
今ちょうどやっ
test.
てるんですけど、卒論でもやってる実験で、
We
こ
have
の
the
サンプラーの
soil
中に土
samples
が入ってま
here.
す。
We are
その土
pouring
に
water
上
into
からこ
the
の水を
samples
ずーっと流して、ここからここに線があるんだけど、
and
この
measuring the
距離をど
time
れぐら
for
い
the
何
water
秒
to
何
go
分
down.
でこの水が通り切るかっていうのを調べ
Then
て、
we'll
土の中の
calculate
防水
a
性
permeability.
を測る実験です。
Hi everyone, I'm Fukada. It's nice to meet you. I'm recording for the lecture of Environmental and Sustainability Sciences. I'm wondering what I have to do in this lecture. You see, they are doing the permeability test. This test uses Darcy's law. Actually, you have already learned. So I'd like to try a new experiment. Do you know Hele-Shaw flow? It's a visualization technique that Mr. Hele-Shaw developed. It reminds me of Darcy's law. Darcy's law says that flux is proportional to hydraulic gradient. We think about a cylinder having cross-sectional area A. Flow rate Q divided by A is flux. Soil consists of so many small grains. Water can flow through free spaces between grains. But we can't consider only these free spaces, so we have to use the entire cross-section. We have to use average velocity over the entire cross-section. Hydraulic gradient is a pressure gradient in the direction of flow. Delta H divided by L. Delta H is a pressure difference and L is a sample length. How much is pressure difference in your permeability test? We need pressure difference to run water. The experimental apparatus is like this. Water column is on the sample. We can see water surface in the column and water flows out of the sample. Height of an upper water surface with reference to a lower surface gives pressure difference. It drives flow. Yes, it's driven by pressure difference. If we raise the upper water level higher, flow will go faster.
高さがどんどん下がっていくから、どんどんゆっくりになっていきますよね、流れが。
Exactly. We can imagine the flow mechanisms and express it mathematically. Hele-Shaw flow is a flow in a very narrow space. It also satisfies the relationship that the velocity is proportional to a pressure gradient. My question is, how am I supposed to make Hele-Shaw flow? Here are two acrylic plates. If I paste them completely, there's no gap to flow. So I use a seed packing. It's like a paper. I stuff this seed between two plates. At the edge, there's no gap, but at the center, there's a gap. Yes, and one of the plates has two channels to run water. One is inflow and the other is outflow. Then let's get started. I built an experiment system. Water is supplied by Marriott tank. It keeps the water level constant. You can hear the sound of air bubble. It means that water flows. The outflow channel has the water surface here. This channel is connected to the flask. Water overflows to keep the water level constant. We can see on water surface a distorted line. Yes, it's higher than the water surface in the left and right channels. We can measure the flow rate using the scale of the Marriott tank. At first, a water level was 22.2 centimeters from the desk. It went down to 21.4 centimeters in 23 minutes. It further went down to 20.9 centimeters in 42 minutes. 1 centimeter corresponds to 18 gram water. Then we calculated a volume of water flowing in each time interval. 14.3 cubic centimeter divided by 23 times 60 seconds. No, I'm looking at measured values. Dividing volume by time gives a flow rate. Flow rate is how much water flows per unit time. The result is about 1.0 times 10 to the power of minus 2 cubic centimeter per second. The third value is nearly the average value. From now, we'll examine the Hele-Shaw flow theoretically. We'd like to get a relationship between flow rate Q and gap size H to estimate H from experimental results. Hele-Shaw flow has already been investigated by researchers. This is a hydrodynamic problem. Why don't we take a look at the theory? Okay. Do you know Hagen-Poiseuille flow? It's a flow in a circular pipe. You know that velocity distribution is like this. How do you explain that mathematically? What does this curve look like? That's right. This curve is a parabola. If we want to express a flow distribution, where should we begin? Velocity distribution can be deduced by fundamental equations. One of them is the equation of motion of fluid. If you have learned physics, you'd know the equation of motion for a mass point. We also have the equation of motion for fluids. We are going to use it to investigate Hele-Shaw flow. It's a flow in two parallel plates so close to each other. Water on a plate can't move, but it can move between the plates.
板の真ん中あたりでは水がたくさん
So velocity must be
だから
distributed.
ここもなんか分布するはずなんですね。どんな、はい、動かな
We
い
usually don't think it can move,
宇宙から大気に
except for very rare air like space gases. We usually think the water on a plate doesn't move unless the plate
付
moves.
着してる水も動かないだろうと考えます。運動の方程式
Now we are thinking about a steady flow.
平常な流れ、さっき小川が
The flow doesn't change.
加速していない
That means the forces are balanced.
保たれてる。おお、いいですね。どこから
That's the question.
二つの力が釣り合って
Two
るから
forces are balanced.
流れが加速しないんだと考える。